and hopefully it will save. If not, we have the backup videos that you have in the Moodle page. All right, so we're going to get started. I just closed YouTube. We're not going to bother with that, and I'm just going to work from here. My participants are showing up on the side. I have participants here. And okay. So we left off in our discussion, unless anybody has a question, I'll take questions. No questions? All right, so we left off. I introduced the idea of a symmetric density curve where the density curve is drawn as a smoothed, idealized version of the relative frequency histogram below. And so we understand three things. First, that the area under the density curve is 1 or 100%. Second, the area under the density curve of any one particular value is 0, because area only exists between range of values. So for example, if I want the density at a particular value just here, we say that's 0 because when x is continuous, that's the case. And for any value of x, the density at the value is exactly 0. So we only compute densities between ranges of values. We interpret the pth percentile is the value such that p% of the area under the density curve lies to the left. So I gave the examples where this position is where 50% lies to the left, 50% of the bars, 50% of the area under the curve are synonymous. And that makes this value, 64, the 50th percentile. Similarly, this value x1 is the 10th percentile because 10% of the observations lie to the left. Okay. And this is just to give me more drawing space, but I fit everything above. Okay. Hopefully you are comfortable with the symbols greater than and less than. If you have trouble with that, please let me know. So fourth point, that I mentioned, not in this order, but I did mention, because density curves are idealized, we imagine that we have all information possible on the variable when we are smoothing out the underlying relative frequency histogram. When density curves are symmetric, and that's what we're focused on, the center of the distribution is the mean, and we use the symbol mu as we would for population data. And mu is the Greek letter for m, or mean. And for the standard deviation, we use the symbol sigma, which is the Greek letter for s in lowercase, s for standard deviation. So far, all I've done is talked about symmetric density curves with those 4 points. The normal distribution is a special type of symmetric density curve. Not only symmetric, it has one peak, and we say it's bell-shaped. So this is symmetric, but this has 2 peaks, right? It's roughly symmetric, but has two peaks. But the normal distribution only has one. And we say it's bell-shaped, that it has a special bell shape is what we're going to get into. What is a bell shape? And what is the particular characteristics? What are the particular characteristics of a bell shape for a normal density? For normal distribution, it has the four properties above. It's symmetric so that mean, median, and mode are all the same. And if we have the data that we interpret as a representative of the population, then we can take a calculation of the sample mean and name it mu, and the calculation of the standard deviation and name it sigma. And then we can draw it. We can draw it, and the most important thing, our goal in statistics, is to alleviate uncertainty. If we believe a distribution of a variable is normal, then it has the following special property. The center is the mean, and at the peak, or from the peak, I have a concave function. It's going to be hard to do, but that should be symmetric. Let me try it again. Actually, I could copy and flip it, but actually, let's do that. Let's and I'm making this harder than it is. Flip. All right, so now, no, that will go there, but I have to erase the bottom. That makes it symmetric. So what we have here is the concave portion. What happens then at one standard deviation? Now for every normal distribution, this is the case. If I move back one standard deviation and forward one standard deviation, and I will use numbers that you'll notice I'm going to use mu as 64 in a moment. For now, we're going to use the symbols. We'll use the symbols, and one standard deviation above and one standard deviation below. Between that range, we find, does anybody know what proportion of the data fall there? What proportion of the bars? You can speak. Bonjour, Paul. Are you still there? Did you want to speak? Maybe he left. No, he's there. He's watching. Did you want to speak, Paul? No? Okay. I'll go back. All right. So anyone?
Professor, can you repeat the question for me, please?
Uh-huh. The question is, one moment, where did my... The question is, What proportion of observations are within 1 standard deviation of the mean? Does anybody know? If you don't, that's okay, then you're learning. So what I'm asking is, what proportion of the observations are between, actually, I won't write it here. I'm going to write it when I have the numbers. It turns out that the special property of the normal distribution is that within 1 standard deviation of the mean, you will find 68% of the data. If you move over another no, sorry, I'm just trying to get the screen I had before. If you move over another standard deviation, so I'm going to do that moving over an equal interval over here. So that's 2 standard deviations away, and on the upper end as well. Don't forget to mute your microphone. Within 2 standard deviations, what happens is the curve turns convex. And how much of the data is within that range? Does anybody know? It turns out that,
93%.
all right, so now you're remembering, or you've seen this before. So it turns out that in fact, 95% of the observations are within 2 standard deviations of the mean. So that's most of the data. Most of the data will be within 2 standard deviations of the mean. Move over one more and another interval, fair interval, equal size. And you'll find this extends. And there's still data after that. That's the important thing. There's still data after that. This should be symmetric or roughly symmetric in the data, that you will find 99.7% of the data. So still, it's almost 100, but not 100%. So what is the case is that a normal distribution is symmetric, single-peaked, bell-shaped in that it has this distribution, allowing for extreme values. So this permits extreme values in what proportion? What's the percentage of extreme values that are allowed in a normal distribution on the lower side? Don't know why I can't. Pardon? 0.12?
0.3%.
Total. But on each side, it's half. Right?
Yeah, 0.15.
Yeah.
Right, so 0.15. So although small, It's a few values that create, there's a few values there that are extreme values. So if you think you have let's say 1,000 observations, or let's say 10,000. Let's make it an easy calculation. If you had 10,000 observations, how many outliers can you expect? So you take 10,000, multiply by 0.15 or 0.3 total.
100.
So 10,000 times 0.3%. So we would write in percentage, that is 0.003. So how many?
That's 30.
30. So in what we call a normal distribution, you can expect that 30 observations could be outliers or extreme beyond 3 standard deviations away from the mean and still be called normal. All right, so that's an implication of this. Of the type of distribution. So the normal distribution was created by statisticians and lots of information derived from it. And it led to the development of a branch of statistics known as Gaussian statistics. And this is where we're going to spend a lot of time in this class because it is a foundation of the frequentist approach to statistics. All right. Any questions so far? So
Yeah, Professor. As you say, if it is normal, that would be like that. But if it is like abnormal in the negative sense, that would have more outliers or less?
Yeah,
anyway?
it could have more, it could have less. It's just not normal. Exactly.
Okay, great. Thank you.
I say normal versus not normal.
Okay.
Now there's many different kinds of distributions that have been defined. I haven't counted them. I thought about counting them once, but almost I know of at least 50 different distributions that statisticians or engineers and people who use statistics use. But this is a foundational, this is where most courses start. Okay, and once you understand how the normal distribution works and you understand more concepts of probability, you'll be better equipped to understand other distributions. All right.
Okay, great. For the 30, as a colleague wanted to ask, for the 30, there is that will be 15.
It should be, yeah. It should be about 15, yeah. 15 on each.
Okay, great. Okay, thank you.
So that's a practical application of the concept of normal. So in practice, if you have a data set, you need to start always making a graph. Once you make a graph, you can make it histogram if you have a lot of data, more than 50 observations I mentioned. And if you see this kind of rough symmetric shape, you can check. You can check how many observations are within within 1 standard deviation, how many within 2, and how many within 3. Okay, and we'll.
Professor, a last question, please. That will be from other colleagues. It seems some of us don't understand the 68%. Where do you find it? I think that would be great if you can.
This is the rule, and it was developed. So a normal distribution was established as a working distribution for statisticians and for statistics. So they made this up, and they made it up in the sense that this 68 represents what we would say in words.
Like a convention, right?
It's a convent, well, it's to use the word most of the observations. So most observations are within one standard deviation, as though, you know, if you had 68% on a test, you know, you got most of it right. You can think of it like that. 68% represents a majority, right? But
Right.
it's definitely not all of them. But then the number 95 again was established to have a great number of them. But then for 3 standard deviations, it detracts from, you know, it remains less than 100% to stress the point that normal distribution allows for extreme values. Now, these are rough. If you roughly approach this pattern in a distribution, you can approximate, you can say your distribution is approximately normal. Doesn't have to be exactly like this. All right?
Okay.
Okay.
This is like a baseline, so you can compare what you have with what is the normal thing, right?
Exactly. So I did, I don't know if you had the chance to watch all the videos, but I provided in the videos. Let me see if I can bring it up. I encourage you, you need to watch them all because they're part of the course. So in this data set, I provided a data set and I asked you to calculate the, you know what, sorry, I'm going to pick up the annotated notes. It's better. It's not here. Let me see if I can get it. One moment. So in these notes for the previous unit, I have provided you some data. How many of you did this exercise? How many of you completed the exercise or watched the video? Okay, so you didn't. All right, so this data is analyzed in video. Let me check the playlist. Okay, I'm not going to check the playlist. All right, I won't check the playlist. Okay, so it's basically one of the top videos, one of the videos at the top. And I give you this data, very small data set, to rehearse calculating the standard deviation and better understand the formula for the standard deviation. And the result is that from this data, you find that the mean is 8.2, which means, let me describe the data set. So the objective here, the goal, was to estimate how much money a student has in their pocket in a given week, on a given day, to spend on coffee or a snack or some lunch. So this data shows that on Monday, the student that was, the data was collected on had $2. On Tuesday, $8. On Wednesday, $10. Thursday, 16, and Friday, 5. So they had a little bit of money, and then maybe they got paid, or they were getting ready for the weekend. They spent money on Thursday, and then they had 5 on the next day. So these are every day how much money the student had as pocket money. And I'm going to use this. It's a small data set. I'm going to use this to estimate how much you can expect the student to have from the cafeteria's perspective or the restaurant in terms of what they're going to offer the customers. So looking at this data, it looks like the data is balanced. You have a middle number like 8. So if I was to put it in order, if I put the data in order, it's 2, 5, 8, 10, and 16. And you see 8 is in the middle. Then you have a value smaller and another one bigger in about the similar distance. This is 3 and this is 2 values, right? Away. Then you have a value much smaller and one much bigger. This one is 6 units away and this one is 8 units away. It's similar. So I'm going to assume symmetry. So we assume symmetry and then we proceed. Remember, we cannot calculate a mean and standard deviation for interpretation unless we assume symmetry or know that its distribution is symmetric. So we'll say it's symmetric, roughly. Calculating the mean, you get $8.20. Calculating the standard deviation, you can do this in Excel, you can do it on your calculator. Please, we did talk about that in the first weekend, so practice that. You would find that the standard deviation here is $5.31. Now, my question to you, and let me give you a moment to try it. Tell me, is this data normally distributed? Now, again, it's a small data set, but it's symmetric, but is it normal? That's the question. So let me give you a few minutes to answer. And I'm going to figure out what happened to all my stuff. My chat. I don't want to see this. How do I get rid of this? All right, now I can see the chat. Thank you for helping. Let me know if you have any questions. So what should you be doing? What are you doing right now to answer this question? So it was determined that on average, this is the interpretation, on average, student has about $8.20, and we say give or take $5.31. That's how I taught you to interpret. So $8.20, give or take $5.31. What does that mean? It means most of the observations will be within 1 standard deviation of the mean. Now we have to check if that means, if that's close to 68. and we'll be on the right track for normality. So if you were to make this interval, what you need to do is calculate the lower end and the upper end. And you get 289. So I'm just showing you with this data set. Make sure you mute unless you're going to speak. Mute your microphone. So that's one standard deviation from the mean. Make sure you mute your microphone. I have to turn that down. Make sure you mute your microphone. So what I want you to do now is, what proportion of observations fall in that interval?
68.
My question is related to the data, it's not normal yet. We're checking.
Okay.
Okay, so go back to the data. So the data says how many between two. So the data was here. I'm going to reproduce the data. 2, 5, 8, 10, 16. How many of these observations fall in that interval?
All of them, except 16.
Over 2.
4.
2
4.
and 16 are out. Just 3.
Yes. Yeah. 3.
And that's 3 out of 5. And what percentage is 3 out of 5?
60%.
Okay, so that's not 68, but it's close. It's not 68. Let's keep going. Now check 2 standard deviations from the mean. Make the calculation without me. Make sure you have your microphones off. There's lots of feedback. You know what I'm going to do? I'm going to turn off my microphone when I'm not speaking. This implies multiply.
Alex Multidor. Turn off your microphone, Alex.
Thank you for acting as moderator.
Oui. Ah, si mon micro est fermé.
So I'm calculating the second interval, 2 standard deviations. This is 2 times 531 for standard deviations, right?
Okay.
Oops. And what do you get? Now you can't have negative unless you owe somebody money, I guess. In this case, there are no negative values, but yet we're going to calculate the interval and interpret. Is that all right?
Yes, we are following.
So this is 18.82. So this is the interval for 2 standard deviations from the mean. Now, what percentage of observations are in that interval?
One hundred 100%.
All right. So that's 5 out of 5 or 100%.
Yes,
So
exactly.
now I ask you, we've just done 2. We've checked 1 standard deviation from the mean. We checked 2 standard deviations from the mean. I would say this does not satisfy, right? Because we need outliers. We have no outliers in this data set. So this data set, it's symmetric roughly, but it's not normal. So that's my example to you. If we were to conduct also the check for 3 standard deviations from the mean, we would get 100%. So my conclusion is this data is not normally distributed. And you make a point, no outliers. Now, maybe if we got more data, we would see it better, but with what we have, we don't have, there's no outliers, and 100%, we get all the data within 2 standard deviation, that's not normal. Okay, so it is symmetric. But not normal. Questions? Okay, so that's my example. That data was from the previous unit. And I encourage you, I hope you can find the time to watch those videos. You do have this week to catch up for the test next week. So no questions? So back to the normal distribution. So that was just an example to show you how we would verify if a distribution is normal or not. And now I want to make some comments about normal distribution. As long as that property holds. Sorry with my, it's hard when I turn the corner to make it straight. What would be required? What would be necessary for these distributions to be considered normal? Both of them. Or roughly normal. It should be the case that within 1 standard deviation, you find 68%. So the curve, the turn should be roughly symmetric. Let me try and get that better. Let's call this distribution A and this distribution B. And let's say A and B are both normal. What do we know? we know that this space has to be 68% and this space has to be 68% of the observations, has to contain. Right? And this,
Mon micro, pas ouais. Pourtant, j'ai fait. Ouais.
what can you say, what can you tell me about the relationship between this standard deviation, this deviation from the mean, and this deviation from the mean? What is their relationship? Do I know anything about them?
I can say that the A is included in B, no?
Not included, but that A has to be smaller than B.
Yeah, exactly.
And what else? The other point is this has to be, if this is smaller and this is wider, and this has to be 68 and this has to be 68, it's necessary that the peak drops down. Do you agree? We have to contain 68% in a different shape. It means that this peak must be lower. So there should be less observations in the modal class. They're more spread out. They're more spread out. Basically, that's it. It's wider. So this has to go down. So the only way A and B can both be normal is if this is smaller than this one, then this peak is lower, implying there's less observations in the modal class of B than A. Remember what modal class means, right? The most frequent class. And this symbol means that these mean the same thing. So it's like Jell-O, you know Jell-O? So I can stretch it to fit in different molds, but with the same amount of Jell-O. The same amount has to be here as here. Maybe graphically it doesn't look like that, but if I insist that they are both normal, then that is the case. So the criteria are 1 and 2, which I've said in 2 different ways. All right. So this is known as the property of normal distributions, or the 68, 95, 99%, 0.7% rule. 68% of the data lies within 1 standard deviation, 95 lies within 2. So we say this means most. This means almost all. And this means allowing for outliers or extreme values. Okay, so that's what you get from those statements. Numerically 68, 95, and 99.7. And why? It's allowing for most, according to statisticians, it's allowing for almost all within 2, and we use that a lot in statistics, but also allowing for extreme value in the amount of 0.3%. Okay.
This is where we think about the outliers, right? The
Right.
99.7%.
Yes, it allows for outliers.
Right.
So that's how you can think, why are these numbers that way? It's for this purpose. Okay, so now, so I gave you this chart here so you can try and draw it. And when you draw it, always do like I did, where you make a dot here and you create an inflection point at 1 standard deviation away. So whatever you do here, you repeat here. Try and make it go. It's really hard on here. I'm more used to Oxford. Very slippery. But there, the point is that at this point, 1 standard deviation away, the curves turn. Make the bell. Okay. You can practice that. You can take a screenshot. I'm going to continue. You want to remember that. Well, just to reiterate, I'm going to reiterate, and then we're going to draw this again. This is 68. Within 2, you have 95. I draw this so many times. Oh, not one more time. So from there to there, you have 95. And then all the way here, you leave 0.15% out here. And 0.15%. So high extreme values on both sides, right? So for outliers in general, for symmetric distributions, in general, for symmetric distributions, we say there are outliers outside 3 standard deviations from the mean. So I'm mentioning that because if the data are not skewed, not symmetric, if the data have a different shape, so they're skewed either left or right, you check for outliers in a different way than you do if you have symmetric distribution. For a symmetric distribution, we say outliers are those that are 3 standard deviations from the mean. When we arrive at normal distributions, we're more specific. In normal distribution, (0.3% of the data are extreme values or outliers. So this is the general rule that you learn in Unit 2, the graphing portion. In normal distributions, it's very precise. You have to have exactly that many outliers, but approximately to say your distribution is approximately normal. Any questions? There, it can fit better on the screen. Okay, so now let's look at some data. And then I'll talk about what I have up here. Here's some data. Here's my example, and this is why I use 64. The example yesterday. Say you have 100,000 as your sample size measurements of height. These were taken from women 18 and over in Puerto Rico. And we found that the sample mean is 64 inches and the standard deviation is 2. Let's say we saw, so we checked with a graph, we took the data and created a histogram and saw a symmetric, single peak, bell-shaped distribution. And we assume from what we saw that the heights are normally distributed. What I want you to do in the space below is depict the distribution. I'm going to give you 5 minutes, so you can also take a break. But take a break and also work on this. Let's take a 5-minute break. And you can try that. I want you to take your break and draw this distribution. This is the symbol for distributed. This N now means normal, the way it's written. And I provide you the mean and the standard deviation in that order. So these are the symbols. That you need. Okay, 5 minutes. Okay, I'm back. How did you do? Did you draw it? What did I expect? I expect you to draw with using the numbers x, normal. We put the mean first and the standard deviation second. Oops, me and my lines. And then what I mark in numbers, so numerically, I write 64 now, and then use equal intervals. So this will be 66, I'm going by 2, 68, 70. And on the other side, 62,
60,
60, right? And 58.
58, yeah.
And now you mark the peak. And then I'll also practice, just to get this right, the inflection point. So this is the same here and here, roughly. And then it begins to turn. All right, and probably left too many outliers there. Let me do that again. A little closer. Maybe even closer. Ah, so slippery there. Okay, so that's how you can draw your own. And then we say within 62 to 66, you'll find 68% of the observations. Let me write that again. So between 62 and 66 are 68%. Within 60 to 68, you'll find 95%. And then all the way
99.7.
99.7%. And outside 0.15% and 0.15 to complete the normal distribution. All right. So we can use this now to make predictions. So this is the idea. This was our goal. We found data. All right. Presumably found data for you. I computed the mean and standard deviation. I made a histogram and I demonstrated that it looked symmetric, bell-shaped. And then I verified that 68% of the observations were within. So 68% of the heights of women were between 62 and 66 inches. 95% of women had heights between 60 and 68 inches. And almost all, leaving room for outliers, 58 to 70, said 99.7% of women had heights between 58 and 70. So that would be, I don't know if you guys are better with centimeters probably, but 70 is 5 foot. Wait a second. 12. Yeah. So it's 5 foot 10, 5 foot 10 inches. And 58 is 4 foot 10 inches, if that helps. Do you need centimeters? So these are, most women are between 4, like almost 5 feet and almost 6 feet. Very rare to find women outside. Okay, it's a very small percentage. So since 100,000 were taken, how many outliers are there in 100,000? How many extreme values?
Should be 100,000 multiplied by 0.3.
That's right.
30.
100,000 times 0.3.
30. 300.
Oh, did we do this wrong last time? 100,000 times 0.03.
300.
It's 300. Because last time I used 10,000 and we got 30, so this should be 300.
Exactly.
So it should be 150 here. I'm going to say short, no offense. 1 in 50, very tall. That's approximately, okay? That's how it works. And I could say very. All right, very good. So then I can ask more questions. I could say, now we can use the symbols that we learn, right? So I could say that between 62 and 66, what is the answer to that question? Now, I already have the answer there provided.
That should be 100,000 multiplied by 0.68.
Right. But no, just the probability right now, not the total.
Okay.
Not how many, but that's good. That's right. So you're going to use 68. In this question, the answer is just 68% or 0.68. And then I can do the rest. I know. So this is what I know. I know also between 60 and so this is what this means. We read this as between. And I recite the smaller number and then the larger one. So between 62 and 66. That's how I read this. And the symbols go small to large. Now I find that my Haitian students have excellent math skills. So I do go slow for the general student, the average student. And I know your math skill is very strong. So if it seems like I'm going too slow, let me know and I can speed it up. So it goes from small to large. The symbols I usually write are like that. Okay, and that. So 60 to 68, that's 95%, or I can write it as 0.95. And then between 58 and 70 are 99.7%. And with these probabilities, you could also calculate the total number if you know the sample size or the population that you're trying to infer. Use that size. All right. So those we all know. Do we know other things? Do we know? Can you tell me? I know your math is so good. And now you have the model. So can you tell me what is the chance that X is between 60, so the heights of women is between 60 and 62. Can you figure that out?
Yeah, that should be 2.7%, right? No.
So let me clear this. Let me clear the drawing so I can illustrate. Make this smaller. So what I want you to do is figure out between these two places. Do we know this? Not directly, but indirectly, can we figure it out?
Be 95.
It's 27,
It should be 61.
Yes, 27%. Yeah.
13, 13, 13,
Okay,
Yeah.
so between,
13, yeah, around 13.
so I'm going to show you one way and then let's see. Yes, you guys are getting it. Okay, you're getting closer.
Yeah.
Mhm.
That,
There's a
that
few
should
different
be
steps.
99%, less than 68%,
So
right?
Right.
95 minus 68
Exactly.
divided by
Yes,
2.
exactly.
Divide by 2.
Right, very good. Okay,
Yes,
so let's do this with 68 in the middle, and then let me erase this. All right, so we have 68 in the middle, but it's total 100. We're going to minus 68, and then we're going to divide by 2. What will we get? If we do that, we are getting this over here. The whole thing. So that will give you just the whole half, right? But I want just the green. So I need to subtract something off. So let's just get that first. So 100 minus 68 divided by 2.
Yeah, 16.
16, right?
Mhm.
Because it's going to be 32 divided by 2, which is 16%. But now I need, because that's the entire half over here. But I
Yeah.
want
Yeah,
just
this is from, yeah, this is before 62 and after 66, right?
right. So I want to repeat the same behavior, the same calculation for 95. I want to repeat the same calculation for 95 between here and here and just get half. Oh, sorry, I went too far. I went too far. I want to just go here. 2 standard deviations. So between, let's make the calculation for beyond here. So that will be 100 minus 95. So I take the inside and I divide by 2.
Like two.
And that's going to be 5 divided by 2 or 2.5. And
2.5.
now I subtract the 2 of them to get the in between. I take the larger number.
Mhm. Mhm. Yeah, 13.5.
So I take 16 minus 2.5, which
13.5.
13.5, which you guys said at the end. So this is 13.5% in here. Very good. So it just took a few steps and some logic, and you can get this. This is not hard.
More steps to get there.
Yeah, that's a few. So it does seem clumsy, a little clumsy, not precise, not exact. So we are going to develop and refine. We're going to refine this approach. All right, that's what we're going to do. However, with this model, you can calculate a few things, right? You can get quite a few things. You know how many outliers there are. You can find areas between any of the large tick marks on here. And in the notes, I have many exercises where you make the calculations. You attempt to do it yourself. Let's try one more. Well, no, let's see. Let me think. Let me go to the notes and see what's there. Let's go into the notes.
Professor.
Mhm.
Hello.
Yes.
Yeah, I don't know if it is an assumption that we can say, I don't know if you can go back, please, to the exercise, to the resolution. Yeah. For example, if we want to get, if we wanted to have for 63, for 60%, I don't know, but do you think we can divide it a little bit?
Okay, so if you have questions
Between
that
62 and 64, for example.
so it's not advisable because you have that curve, right?
Okay.
This
Okay.
curve, it does not
Yes.
even. So
Okay.
we need a more precise approach. This is just a rough these are approximations really. And you could, I mean, you could try 63 in here and figure something out. But there's a better way, and I want to teach you the better way. But before we go to the better way, I just want to do a few things in the notes. So I have many questions pertaining to that graph in these pages here. These pages, I ask you to calculate x is greater than 66. X, would you like to try a few of these together?
Okay.
Okay, so try a few of these. And again, these are most of the pages here are in videos online, but let's try a few together and then you can finish this week practicing. So let's try this one. So I'm going to draw my curve. That was terrible. Let me try that again. And I know 64 is in the middle, and then 66 is about here.
For the first one, that should be the first step you did. Right.
Right, one standard deviation away. So yes, it's just the first step that I did, that I know this is 68% in the middle. So outside is 100 exactly minus 68 over 2 will give me 32% divided by 2, or 16%. So it doesn't look like it because it's just a sketch, but that in a normal distribution, this should be 16% of the observation. So you imagine under there is a relative frequency histogram. Okay, so you get the idea. These problems are not so hard. I'm going to try
0.15.
exactly. And this one, why don't we try number 3?
Okay. Number 3. For me, that's supposed to be like 97.5%.
84%. It should be 100 minus 16. That will give you 84%, I think.
Yeah, for me, that should be 97.5%. I don't know, but because on the left, between 95%, you have 2.5%, and on the right, you have 2.5%. So that's supposed to be wide 60. So that's supposed to be, for me, yeah, that's it's 5 under 2, so 2.5%. Yeah.
Yes,
Exactly.
yeah, exactly.
Sorry, do you not hear me? I touched a button. Okay, so only 2 numbers are needed to make these predictions. That's pretty amazing. So that's what we use. Mean and standard deviation, we write it like this, and then we can, whatever we're interested in, we can make predictions. So this is the probability that a woman is taller than 5 feet is very high, 97.5%.
Yeah, exactly. It is like the second step you take. Related to the second step.
Yeah, I just added it. Yeah. Okay, so there's many other problems here that you can try that are similar. I want to differentiate the different problems. So let's look at these two. Now, if you have any issues about these, you can let me know, but I need to move on. Oops, I don't want to use that. I want to use the pen. So what's the difference between these two? Let's solve 70, and then we'll talk about the other one. So this is going to be 64, 66, 68. Notice every time I draw it. And we know that number. We already calculated that, right? What is that going to be? This is 1 standard deviation from the mean, 2 and 3 standard deviations from the mean. So this must be right. So this is a property we learned about outliers. So the chance is 0.0015 or 0.15%, we write. It's very small. So it's very small chance that a woman is almost 6 feet. What about this one? What's the answer?
It's the same thing.
All right. Why is that?
Because for the percentage for a number is 0. Yes.
So, yes, because the
Yeah.
percentage, the value, the density at a value doesn't exist, or sorry, we say it's 0. It's unlikely to be just at one value. So it doesn't add anything to the density of 0.0015, which is already really low. We get the same answer. All right, so writing it like this, which you'll see in some textbooks and even in my notes, or like this, when a distribution is continuous, that's the fact. All right. Good. And so the rest, you know the answers for those, and you can ask me if you don't know. I'm sorry, I'm going to move on. If you take a screenshot, I can move on. We are recording the video, so you can watch this later. Okay, now what about this problem? How do we solve this problem with our tool?
Sorry, before going there, I don't know if we can try the 82. It is not, I don't know.
8?
Yeah,
What is 8?
X equal 82. That should be,
What should it be? It should be
0.
0 again. Yeah,
Yes, 0.
always 0.
exactly,
Because
0.
it's continuous variable.
Exactly.
Exactly, always 0. Okay, and let's try this. Let's try these. Now I put asterisks because I want to make a point to you. So let's try the first one, and then we'll get into the ones with asterisks. What does this mean?
So,
X is an outlier values.
for me, that's supposed to be like, if it is like 0.95, 97.5, that should be more than 70.
So that's okay. So let's review. So first of all, I've written this problem differently than I have today in the other exercises. I've written this as we did the other day, yesterday, we discussed this means that X is what? What do we call X here?
X is a percentage 95, 97%.
Yeah,
Right.
97.5. Yeah,
97%, yeah, percentage.
right. But that should be 70, something like that.
Yeah.
So it means that X is the 97.5th percentile. Now allow me to draw this. And so this will be here, and this will be 9750, let's say. and this is x. And the question is, what is x? That's the question. You need to relate this drawing with the one that we know already, that we've already subdivided. And we saw this number already. Do you remember?
Yeah,
Yes.
that's supposed to be like,
So let's go back. Let's see where we saw that number.
The two times. The two times.
At
Yes.
60, right? The third problem, it was
Yeah.
greater than 60, it was 97.
yeah, exactly. But it-
Yeah.
So it needs to go the other way now. It's symmetric, so if it goes the other way, 68, it will work. So this, again, we're kind of fumbling through, but we can find the answer.
68, yeah.
Okay, so this would be 68, and then this one would be 64 or 66, and this one would be 64, etc.
Mhm.
That's how we would find that. So some students don't feel maybe comfortable with what I'm doing right now, and that's exactly how I want you to feel. I don't want you to feel like, oh, you know, if this is statistics, this is going to be easy. I mean, you're kind of fumbling through it, and it's not hard. The mathematics, the arithmetic is not difficult, but it doesn't feel very systematic what we're doing. Every problem is slightly different, right? So we're going to develop a more systematic approach to solving problems in a moment. First, I want to stress and emphasize why we need that. So here's a problem like you mentioned, someone mentioned, what if we're not on the larger grid of 1, 2, or 3 standard deviations from the mean? What if we're at 55 and 65? How do we compute that? Can we do that? Well, I put an asterisk there to say, well, you can do it, but it's not recommended. It's just an approximation because
Yeah.
our larger tick marks at 64, 62, 62, 64, 66, 60, 58. And 55 will be here somewhere. And 65 will be here somewhere. We could guess, right? But this curve, oh, it's 11 o'clock. This curve is the problem. So instead, for problems like this and problems like this one and the other, where they're numbers that are off the chart, this one's not exactly off the chart, but the question in the second, the second or the lower problem here, I'm asking, find me values where 68% of the observations rest between. So yeah, we know one place where there's 68% of the observations. We know that within 1 standard deviation,
Yeah.
there are 6.
Mhm. That should be between 62 and 66.
Yep. But aren't there others? I could find infinitely many numbers, let's say between here and here somewhere, where there's also 68% of the data.
If we move the graph, the curve,
Right?
probably.
If I move along the curve,
Exactly.
but I don't know where those numbers are. So how can I develop a more, you know, for values that are off the larger grid line here or tick marks, what can I do? So what statisticians did was they actually have the function. They created this function. This is the actual function. Now, I'm not going to ever mention this again. I'm just going to mention it now for people who don't like functions. But many of you are professionals that work with mathematics, so this doesn't bother you. This is a function representing the normal distribution. And you notice, you see some things that you're familiar with, maybe the pi symbol, the exponential function. But what you see in particular is the importance of mu and sigma in this formula. So the formula is it plots on the XY axis, the coordinate plane, and it will make this shape for you. The shape will be determined by the value of where you are, X, the mu and the sigma, okay? So statisticians can use that, and using integration, they can actually calculate the area under this curve anywhere for any X. And that's how they generate results, okay? So they can be very precise to fractions of a number for X. Okay, any questions about that function? You have been given a table so that you can imitate what a statistician would do in making more precise calculations. Also, I'm going to show you how to compute these values in Excel. All right. You might also have a calculator that does these calculations for you. So we're going now beyond the 68, 95, 99% rule to find values or percentiles for any X. But also we can get values, we can get the chance of certain observations between ranges of values using the techniques we've already discussed. If you get the larger one, you can find the area in between by subtracting the area to the left here. All right, so remembering all of this is the density curve. That's an idealized version of the histogram underneath that represents the ranked data. So hopefully you're still following along. So at the end of these notes, I have a table that I need to teach you how to use. But in fact, you do have access to Excel, so I'll teach you how to use that too. So in this table, so this table is on page 23. And I recommend you print, if you don't print all the notes, you at least print this table so you have it at your side. So this table provides you the values for Z. What is Z now? This is a normal table, but this is called the standard normal table. The standard normal curve. So far we've learned about symmetric distributions, and we've learned about normal distributions as a special type of symmetric distribution. And a special type, sorry, a normal as a special type of symmetric distribution. And then standard normal is a specific normal distribution. It looks similar, right? It's single peaked, bell-shaped, and it also has the properties of the 68, 95, 99.7 rule, which I'll demonstrate. Or let's try that. Let's check. We're going to check, and then I'm going to talk about where this comes from. So in the standard normal distribution, it has a special, because we use it as standard, we give it a special symbol, not X anymore. We're going to use Z or Z. And the little z represents the values, or they call them Z score. And the curve is the big Z, or capital Z. Okay. And let's check. Z is distributed normal with a mean of 0 and a standard deviation of 1. So those are its parameters and what make it special. So within 1 standard deviation of the mean should be 0. We should find 68% of the observations. So how are we going to do this on this table? This table only gives you, within the table, it only gives you the left side as demonstrated in the graph here. So if you provide it with the z, it gives you the area to the left. So in other words, inside the table is the area inside the curve. So we begin with this value here, 3.4 negative. The area to the left of negative 3.4 is this amount, 0.0003. So that number appears, and say it's very small, so it's like here somewhere. I'm going to make this bigger and write that down. So the table begins at negative 3. What is it? 40. I have to check. Sorry. Negative 3.4, right? 40. Of course, because, and it would be here somewhere. And the area to the left of that is so small, it's 0. It's a very small amount. Right? Invisibly, you don't see anything here, but it's a very small amount. The other extreme, what is the largest number on this table? What is the largest z-score on this table? If you go to the bottom, the largest number on this table, I'll refer to as the negative table, will correspond with 0.5. So it's going to be 0, you see? So to arrive here, you read the table from right to left. Because what we're doing is working with negative numbers, and we're going from negative to 0. And the highest number, let me show you here. The second digit, let's look at the second digit. The highest number, or the lowest number, okay, so the highest number is 0 on this table, and the lowest number is negative 3.4. Let's correct what I did before. What's the lowest number? Anybody tell me? I have to correct what I did before. I just showed you the first number, but that's not the lowest. The lowest number would be negative 3.49, which is here. And it has it's even smaller than where we were. Its area to the left is 0.0002. So this table goes from negative 3.49 in second digit all the way to 0. And it gives you the area to the left for all of those values, okay? The second table continues, and it's all the positive values. To read this table, you have to work going left to right, like how they read in Hebrew or in other languages, Mandarin. Okay, so you're going left to right like this. Let's continue to the next table, and then well, let me just make the note that here at 0, the area to the left is 0.5, according to the table. Okay, let's continue. The next table is the positive table. You see, so with this table, we begin at 0. This is more straightforward. We begin at 0, 50%. And what is the highest number on this table? What is the highest Z score on this table?
Let's get down, yeah.
0.0559.
The highest?
It's 3.4.
3.49.
Plus, plus 9, yeah.
Yeah, so the digit, this axis gives you the second digit.
Yeah, you should add.
Yes.
Yeah.
So we end up at 3.49, and the area is 0.9998, I believe. Let's double check.
Yeah, that's what I said.
That's right?
Yeah.
All right, and it goes until 0. Oh, I'll put it red. Okay, so this table goes between 0 and 3.49. Now, depending on what you want to compute, sometimes the table will be sufficient. No, the table will always be sufficient, but sometimes you'll choose the table and maybe other times you'll use Excel. So let's this table for the standard normal will give me calculations of likelihood or probability for the standard normal distribution. So I'll use the Z symbol for the lowercase z score, just to differentiate from the uppercase curve, okay? So I can ask you questions. I could say, what's the probability that the curve is less than 0.85, and what will you tell me?
It's 0.80.
85.
82, yeah, exactly. 0.80.
So 0.85
Yes.
will be here,
Yes.
right?
Yeah.
So 0.8023.
Mm.
Okay, so let's replicate that in Excel so that you know how to do it. So before I do that, let me differentiate the z-score and the probability. This is different. All of the probabilities will be less than 100%. So this is the percentile or the probability. And I know that because I asked for it. You see, remember Remember, the P means percent or probability or proportion or relative frequency. And this other number that looks similar, but it's not, is the z-score. Okay. So let's do this in Excel. I don't know why this is not there. Sorry, one moment. I don't know what happened there. No, what's happening? Get out of here. Let's see. Okay, I'll just open something. These are big files. I don't want to. I'm not sure why this opened up for me. Here we go. All right. I want to calculate at 85.85. So I put my cursor in here and I use the equal sign. And I say equals. And I want to use the standard normal. So I have to write, usually on Excel, now it looks a little different here. You get a drop, when you start writing, a drop comes up for the functions that you have. So here we have for normal, if I start writing, oh, you can't see. Can you see now? So when I start writing normal, it shows some options. Which one do you think I use for standard normal distribution? Let's see if we can get your intuition working.
S distribution.
Okay, so nominal is not it.
Norm. That
Norm
is
distribution would be for a regular distribution, but this is the special one. This is standard normal. So I'm going to go to the last one, S.
Mhm.
Exactly.
Okay, and I'm going to put in here under Z. I need the, okay, under Z, I put the number 0.85. All right, and so that'll give me the area to the left. I have to tell it I want the cumulative value, meaning I want the area to the left. And you do that by indicating a 1. So that's just the way it's done. If you don't want cumulative, you say 0, and I think it'll give you the other side, the inverse. Actually, we can check. So let's, is everybody ready? So norm.s.dist is the function that you enact when you put an equal sign first to denote function in Excel. And then there you go, same number, more precise even. In Excel, you can get as many decimal places as you want. Any questions?
I will need some explanations, not with Excel, but as we did it during the exercise earlier, please.
Oh, the other thing that we did? Okay. So here, this table,
To get that, yeah, that number. Yeah.
looking up the number, we went to 0.8 and then here 5 for the second digit. That's how it works. Got it? 0.85. And then this is where I pick up the answer. I'm not sure why this bar is here. Why is this bar here? It's not showing on mine.
Professor,
Okay, it's gone.
Professor,
Yes.
I can say the first column is like the stem, and the
Yes.
first line is like the leaf.
Exactly. First digit, second digit. Exactly.
Yes. Yeah.
Thank you.
Okay.
Okay, so let's go back to Excel and confirm. There you go, same number. Let's check what happens if we put 0 instead of 1. I'm going to copy. I'll just do it again. So let's do it again. Equal, and I start to write. Ignore, and I see the options, and I can scroll through. Whoops, I got many options. No, that's not the one I want. I'll explain that one later. That's not it. I want nor this one, S. Standard distribution, exactly, standard normal. And I mentioned 0.85. This time I want to say not cumulative. So I'm going to use 0. What should I? Ready? So what do I get when I put it 0? What is it giving me?
It gives the left side.
Exactly. It gives me the left side. Very good. I don't know why it's getting dots. Why is it making dots? Oh, I don't know what's happening. Sorry. Undo drawing. Oh, I think I hit the draw button. Oh no. Here, there. All right, so it gives me the left side. So this one gives me the percentile. That's not what I want. Right? It gives me the left side. And then the other one gives me the upper or the right side. I don't know why it's doing this. Oh my goodness, I don't know. I'm gonna have to type it. I think you get the point, right? Got it? So what did we do? We typed 85, sorry, the value and then 0 for cumulative. And here we type the value and 1 for cumulative. So you get lots of information from Excel. Okay, so that's what we know how to do with this table. What else can we do? I was suggesting we should verify. Let's verify that the standard normal distribution. So here it is. Verify that what I'm going to call the Z table of the standard normal distribution has 68% of the observations within 1 standard deviation. Oh, I shouldn't be using X. I should be using Z, right? I'm going to call it Z. It's a special distribution. It has a special name. All right. So what should be the values for 1 standard deviation from the mean? What should I put there? Remembering anybody? What are the numbers here? How would I write this? I'm going to write it like this. And what are the values? 1 standard deviation from the mean should be what? Anyone? You there? What values should I put here for 1 standard deviation from the mean? So let's draw the standard normal.
Minus, the first one is minus.
Right. Let's draw the standard.
Minus 1,
For people who are hesitating.
minus 1,
Right.
1.
1 and 1.
Yes. Minus 1, 1.
Okay. And then 2 standard deviations would put us
Minus 2
minus 2.
and 2.
Yeah, and 2.
And then the 3rd standard deviation will put us
Minus 3
Plus 3
and 3.
and 3.
Very good. So we see now why, I hope you see why the standard normal is useful. Where I am on the curve aligns perfectly with the value given for Z. That's not the case in the regular distribution we were looking at. So when we had the example for the X being normal 64, 2, what was in the middle was 64, and there was 62 here and 66 here. The number didn't tell me precisely in one, in a simple way where I am relative to the mean. I would have to make a mental note. But here, if I tell you the Z-score is -2, where are you? You are 2 standard deviations below the mean. So the number itself tells you the relationship to the mean. Remember, I told you the importance of statistics is that, or what statistics is about, is expected values and relative measures. The Z-scores give us a relative measure relative to the mean, the expected value. So if I'm at 2, where am I? What would you say? 2 standard deviations above the mean. If I'm at -3, where am I? 3 standard deviations below the mean. If I was at 0.85, where am I? .85 standard deviations above the mean. This is very important. So I'm going to give you, let's try, I'll give you 5 minutes. Well, give me 10 minutes. No, we're going to finish at we're going to finish in a half an hour, so I won't give you a long break. Let me give you 5 minutes to try, at least do the first one. What I want you to do is verify these. How would you do that? Using the table or even using Excel. I'll give you 5 minutes to take a break and think about it. Okay, I'm back. So I made some notes to emphasize what I was saying. The number corresponding to the position on the number line for the Z distribution also happens to be where you are relative to the mean. So 3 means 3 standard deviations from the mean, and 2 means 2 standard deviations from the mean. And that's not the case in general normal distributions. So how do we check this? How do we verify that we have a standard normal distribution? So let's see if I can take each one at a time. So how would I calculate this? I'm going to draw the curve. You should always draw the curves, okay? With a 0 here and -1 to 1. Now, we know the answer should be about 68. At least approximately, or to just 2 decimals, right? 0.68. But let's check on the curve. Let's check what this would be for -1 and what the percentile would be for 1. So let's do that. Let's go to the table. So for 1, so -1, we scroll up and we see at -1, the value is 0.1587. So let's put that on our chart. Where did I start that? Oh, it's not in the notes, right? Because I have to scroll back. Okay, so I'm going to have to do this with a table. All right, it's over here. I have it after. So this is 0.1587. 0.1587 underneath there. But I want the area in between. That's what this symbol means, the between. So what I need to do is get the area to the left of 1. The area to the left of 1 is here, and it's 8413. 8413. So I'm going to write that down. And now what I'm going to do is take the larger number minus the smaller area to calculate the area in between. And what should we get? We should get 68, and it looks like it will be. But I'll have 4 decimal places because the table provides 4 decimal places. It's more precise, right? But you round it to 68. So that's true. And you can check it for the others as well. Let's try 2 standard deviations.
Approximately 95%.
It should be approximately 95%.
Yeah.
Let's verify. Oh, you already did it? Okay. So let's get the values from the chart for -2. For -2, the value is up here, 0.0228.
Now for 2.
Yeah,
For 2.
yeah. For 2, you find it is going to be 0.9772.
Yeah, 9. Yeah, exactly. 9. 7.
See,
And now we
Yeah,
subtract
no
them to
problem,
find
no
the area
problem.
in between.
We should make the difference now.
Now you make the difference.
Fais ça, non, pas un problème, non, c'est bien. En forme, yeah. Pas un problème, il te dit ça déjà, c'est pas grave, c'est bien. En forme, Kiki, yeah.
Ernst, tell me cool.
And you get 0.9544. Again, it's approximately 95%. So yes, this is true as well. So this distribution and the chart that accompanies it, it's normal so far. We'll do the last one before we go, just for completeness. So we're proving that the standard normal is normal, and we've provided much more detail than we had before, simply using the 68, 95, 99.7% rule. Let me do it in this corner so everything is together. I'll do the same thing over here without changing the page. Draw a picture. And looking on the table, -3 is, scrolling up, -3 is here. 0.0013. And for 3, it is much larger, 0.9987. We want the area in between, so we must subtract the larger one by the smaller one. And you will get 99.7. Do you see?
Yes.
Very nice. So, what did we learn before we go? So we have learned about, uh-oh, what happened? Hold on. There we go. Everything in one page. We have learned that a standard normal distribution is a special kind of normal distribution. We learned how to use the table, and I've also shown you how to make calculations in Excel. Whichever one serves you is fine with me, all right? What I have to teach you in the afternoon then is how to make calculations, not just for probabilities. That's what we've been doing so far. I'm going to teach you how to make calculations given a probability determining the percentile, so the actual z-score. Then we're going to use this standard normal to solve all types of normal problems regarding normal distributions, because there's a relationship between normal and standard normal that has to do with the link between this graph and this graph. So with that, I'm going to wish you bon appetit. You're going to eat something. I'm going to eat something. And we will see you in 2 hours. I'll stay back and answer any questions that anyone has. So you can ask me your questions. If not, you can just go.
Okay, bye.
Bye-bye.
Okay, thank you.
Professor,
Yes.
Professor,
Yes.
I still I'm not really, I still have some kind of trouble to understand for the table Z table, like when you were talking about the 0.05 and not what you just did, but the first one when you were talking about when you were comparing what you find from Excel and the 0.8200 something
Yeah.
like that, but not this one, but you did that before that. Yeah, exactly. This number. I don't know how can I find it on
In
the
the
table without doing it in the Excel. Yeah.
0.85.
Yes,
Use
exactly.
the z-score. So go to the table and look on the table for 0.85 on the margin. So you go here and find, look, point.
Exactly. Yeah, on green, 0.8. Yeah, I don't know how can I find it quickly because I don't know what it comes from.
It comes from and you mean in the table or from how did the statisticians figure it out? It's
Yeah,
the
exactly. On the table. How can I get it?
It's the area under the curve. It's the black here.
Yeah, exactly.
If I made z 0.85, that's the black. That's what it is. The percentile. The number is the percentage of observations with the bars under the curve.
Yeah, how can I calculate like the p factor from z less than 8.85 that gets 0.80.
Well, you use the table, or you have to do calculus. You have to use the formula, which I'm sure maybe you can, calculus, but that's where it comes from. It comes from this formula here. Where is it?
The z, okay, x minus, okay.
I have to find, there it is. It's this formula that they're integrating.
Oh, okay.
So what they do is they integrate with.
Okay.
Does that make more sense?
Yeah, I see.
See the math, the abilities of my Haitian students, excellent math skill. You need to know actually the formula. So this is the formula that will give you the area under the curve.
Okay.
Now this is the red here, the red. So that's what it is.
Yeah, okay.
Okay. Good, thank
Yeah.
you.
Yeah, thank you.
Anybody else? There's still some people here. If you want to ask me questions. Samuel, oh, I see, I didn't even watch the hand up. Samuel, did you ask your question? Sorry. I've been
Yes,
forced.
I just asked you it. Yeah,
Okay.
that was me.
Okay, thank you.
Thank you.
I have to watch so many pantallas, so many screens. I have to get used to it. So did you prefer this Zoom class? Or do you prefer?
I think it is better because now we can participate with you, and I think we are more concentrated in the
Okay.
course instead of writing something on YouTube. YouTube is like sometimes we are a little lazy, like we are tired a little bit with it.
Yeah, so yeah, so
With
you want
Zoom, we can participate, we can discuss with you.
faster.
That is better.
Okay.
So we want sleep. I can say that. I like that.
What I want to know is, yeah, I see. What I want to know is this, if I pause this, I have to make 2 recordings, right? If I shut this, I stop and the recording will stop, right? And then I'll have to make a second video this afternoon, I guess. The only,
Teacher Teresa,
uh-huh.
can you send us the files after the class, please? So like you resolve the problems on it. Can you send us the file with the resolution?
I can send you the files, but you have all these files. Well, anyway, if you want the marked up files, I can send them, I guess. Yeah, I don't
Yeah,
know.
exactly. He was talking about the resolution, like with all the solutions you did.
Yeah, the only problem is I
The
don't know
markers.
if I deleted any of them.
Okay.
And they're big files, so I don't know how I'm gonna give them, like, they must be large because marking them up with all that, I don't know. We'll see. I'll see if I can do it.
Okay.
See if I can do it. Yes, yes.
For me especially, I would like you know that I am still unable to access the community in Linnea. So I received your mail this morning. Each time when I try to access to the platform, to the Universidad Comunidad Linnea, they tell me that my username or password are not good. So I try again. It doesn't match. So as I wrote you yesterday or the day before yesterday, I don't remember. This is the main problem.
I
So
see. So you need the note.
again, I try to access to the Comunidad Linnea. They tell me the same thing. I don't know what should I do.
Maybe, well, I want to meet with you. Maybe after the class today, we can meet and
No problem. No,
you can share your screen and show me your input. The issue with on my side is the administrator is not, you know, he's a professor, but he's not my staff or anything. I cannot control him. And
I will try right now, and I will send you the
screen.
screen.
Send me the screen.
I will do that right now.
Okay.
Okay.
Okay, thank you.
Thank you. Bye-bye.
Bye-bye. See you at 2 p.m.
See you.
Bye.